Okay, this chart is about terminal speed. So as an object falls from rest in air, um, the downward speed increases. And as the downward speed increases, the air molecules it hits, um, it impacts with a larger and larger speed. And so the physics of this is that the molecules, the air molecule collisions become more and more violent as the object picks up speed and the upward drag force increases. And so if you start at rest, there's only one force acting immediately after dropping the object. There's only one force acting on the object, and that is the downward force of gravitation. But as time progresses and as v picks up magnitude, downward v, the magnitude of the drag force becomes larger and larger, and eventually the drag force becomes equal in magnitude, but of course opposite in direction, to the downward gravitational force. In which case, the net force is zero, the acceleration is zero, and the object has thereby achieved its terminal velocity. And so just to summarize all of that, v increases until f net is equal to zero, at which point d vector minus fg vector is equal to zero. And that, of course, means that 1/2 c rho a v sub t squared is equal to mg. We can solve this for vt, and we thereby get an expression for the terminal velocity as a function of the mass of the body, the gravitational constant, the c constant for the shape that we're assuming, the air density, and the cross-sectional area of the object. So what's interesting here is we can take two quite contrasting objects, a baseball and a ping pong ball. So what I'd like you to do is I'd like you to look up the data on these two objects, and I'd like you to compute what the terminal velocity is for a baseball and for a ping pong ball. Okay, so I'll let you do that. You should stop the YouTube and do that now. Just get on Google, and what you'll need for the baseball is the cross-sectional area, um, and its mass, and then for the ping pong ball you'll need similar data. Okay, so assuming that you tried this by yourself, the data for the baseball is that it has a diameter of 74 millimeters. So the radius is 74 millimeters, which I'm expressing as 74 times 10 to the minus 3 meters divided by 2 squared. So its cross-sectional area is 4.3 times 10 to the minus 3 square meters. Its mass is 145.5 grams, and that's 145.5 times 10 to the minus 3 kilograms. And so V sub t, putting the numbers in, 2 times 0.146 times 9.8 meters per second. And I'm going to use a 0.5 factor as appropriate for a sphere, 1.2 kilograms per cubic meter for the mass density of air, and the 4.3 times 10 to the minus 3 square meter cross-sectional area, and that gives 33 meters per second, which when converted to miles per hour is 74 miles per hour. What's interestingly, if I look this up on Google, um, the terminal velocity of a baseball is more like 95 miles per hour, which converts back to 42 meters per second. And that must mean all the other assumptions are okay, but the c value that we assume is too big. It must be a smaller c corresponding to a bigger v. And that has to be because of the stitching. So the stitching is giving the baseball some aerodynamical features. It's not just a sphere. Ping pong ball is just a sphere, but a baseball is not. So let's compute what C would have to be to do that. So that's what this next part does, and I'll let you follow the algebra here. But what I come up with is that a C of 0.31 instead of 0.5 is what um, gives a prediction of 95 miles per hour. Interesting. So for the ping pong ball has a diameter of radius of 20 millimeters, diameter of 40, radius of 20. And so a cross-sectional area is 1.36 times 10 to the minus 3 square meters, 1.26 times 10 to the minus 3 square meters. The mass is 27 grams, 27 times 10 to the minus 3 kilograms. And so if you plug the numbers in there, there's no reason to use anything but 0.5 on a ping pong ball that has a smooth outer surface, no stitching or seams or anything. There is a seam on a ping pong ball, but it's if you run your hand over it, you can't feel anything. And so this comes up to be 8.4 meters per second converted to miles per hour. It's 19 miles an hour. So this has a major impact on the sport, somewhat like badminton. When the ball is hit, it's initially the way professionals play. The ball is going quite fast, I'm sure faster than 8.4 meters per second, but it immediately starts to slow down, as also happens with a shuttlecock in badminton if it's hit hard.